Hi, our presentation topic is on object detection with region proposals method. The way we have structured this presentation is we'll introduce the motivation first on why we did this presentation. Then we go on to talk about the traditional methods and the related work with object detection. Later on, we move on to the more modern methods of detection, which is RCNN, fast RCNN, and faster RCNN. These three are our major papers for the presentation. And in the end, we also have carried out implemented these methods on a custom data set, which I created for the motivation, for the task explained in the motivation. And in the end, we give final thoughts and inferences on all the three papers. So the motivation here is in trauma cases where there is an accident, the patient is immediately rushed to the emergency room, and the first thing a doctor does is do a fast scan. A fast scan is basically doing ultrasound scan at these 4 points. So when you do a fast scan at these four points, you know if there are any internal injuries. So our solution to this problem is have a robot in the ambulance itself which can do the fast scan, and the radiologist can control the robot, or the robot can do this autonomously. Now to do it autonomously, the robot will first have to localize itself with respect to the patient, and for that to happen, we need to detect the umbilicus, and using this the robot will be able to localize itself with respect to the patients. Now we also don't want the ultrasound probe hitting the patient in wounded region or on banded region, and that is why we need to detect wounds and bandages as well. That is how we propose that the aim of this problem is then to detect the umbilicus wound and bandages accurately. Now Darshan will take over.
Hey everyone, the objective of this presentation is to find a object detection algorithm which does this job more accurately and use those results for the applications of classifying wound, bandage, and umbilicus area for autonomous fast scan. The traditional methods for doing this includes hog-based sliding window, selective search, and exhaustive search, which are not that accurate and neither that fast enough. With the rise of deep learning networks, we have more traditional ways of doing this, which include RCNN, SPP, fast RCNN, faster RCNN, and so on and so forth. Specifically for this presentation, we are going to limit our talk to RCNN, fast RCNN, and then faster RCNN. We're going to touch some grounds on selective search for object recognition. So let's dive into it. Now going over some terminologies before we actually get started. We have semantic segmentation, which is a pixel level classification wherein we classify each pixel into their respective labels. Then comes classification, wherein we take the image and say what the image is. So in this example, we have a bunch of sheeps here. So we just get the output as we have sheeps. We don't know how much it is. We don't know where they are. Then comes localization, which gives us some more data about the location of the object. So it draws a bounding box around a particular object. So we know where exactly the object is. But again, we don't know how many objects there are, or we don't have information on what the object is. A combination of classification and localization is given in this image here. Taking it to the next level, object detection gives a more distinct information about how many objects there are in the image and where they are present. Instance segmentation is the same as object detection, but more at a pixel level information. So each pixels are divided into are classified and located where they are and what class they belong to. So moving on to our major focus here, which is regional convolute neural networks. So which is also known as RCNN. So RCNN is one of the most significant papers in this field because they were one of the first uh, papers to talk about a usage of deep neural networks in this application of object detection. It's quite intuitive, in which it consists of 4 steps, which is region proposal, convolute neural network, uh, class linear SVM, and filtering those results using a greedy non-maximum separation. The architecture for regional convolution network is pretty straightforward. We take an input image such as this one, and we do something called as region proposal extraction. In region proposal extraction method, we generate generate a ton of images, each of which of different window size, and we basically determine if the object we're looking for is present in that particular window or not. So keeping that in mind, there are several methods which do this job for us, such as selective search, category independent object proposals, multi-scale combinatorial grouping, etc. It doesn't really matter which method we use for this purpose. Uh, we just need a lot of images of different window sizes. Each of these windows are then wrapped according to the requirements of the convolute neural network, such as AlexNet in this example. And these wrapped regions are fed forward and are passed through SVMs, which are individually trained for each class. So we have a different SVM for each of these classes, such as airplane, person, TV monitor, etc., which gives us a positive or an affirmation or negation if that class is present in it or not. Once each of these wrapped images are passed through convolution network individually, the output is filtered using greedy non-maximum suppression, which basically compares the IOU, which is intersection over union of each of these objects with that of the learned threshold. If the IOU is any less than what we need, it is rejected, and the one with maximum is passed through for the next one. So this way we get just the right segmented object, and that's how we learn the neural network. Let's look at how exactly so let's see how these region proposals are made. We have this algorithm called selective search method, in which the basic underlying idea is that we look for uh, we look at the image through window sizes of various different sizes and scales. So we search for features at different image scales, such as these examples here. So we for each different scale we find features, and the set of pixels are grouped together based on similarity in texture, shapes, sizes, and so forth. So as you can see in this image right here, there are hundreds of these pixels recognized at various different scales, which is exactly what we need. So moving further, the dataset we are using for this particular presentation is the Pascal's visual object class, which consists of 20 object classes and about 9,000 different images. We've decided to fix on one particular dataset, so it'll be much easier to compare results of various different methods for the same dataset. So coming to the next part, which is training, we use a pre-trained network for our CNN. In this case, we use the AlexNet. To adapt the CNN to the new data and new domain, we perform fine-tuning of the parameters in this particular CNN. Apart from replacing the CNN's ImageNet-specific 1,000-way classification layer with a randomly initialized n+1 classification layer, the CNN architecture is really unchanged for the most part. So it's just reduction in the number of classes, and we treat all the image proposals with IOU greater than 0.5 as a good ground truth, as positives, and the rest are assumed to be negatives. Testing. So for testing, we run selective search as discussed in the previous slides. We extract 2000 region proposals, wrap each image and its path through CNNs for the feature computation. For each class, the score feature vector using SVM is trained for that class, and a greedy non-maximum suppression rejects a region if it has an IOU overlap of that is greater than the learned threshold. Which is a really important part here. The overall idea of the paper is very interesting. It seems that the natural extension, it seems to be a natural extension of the previous methods, which is in a proposed regions, extract features and classify regions, except that the feature extraction and classify the regions is replaced by, instead of traditional methods, it's replaced by neural networks and SVMs. So before we discuss our actual results, let's take a look at MAPs, which are a very significant factor for measuring the performance of a object detection or object detection algorithm. So MAP is a average of maximum precisions at different recall values. Now notice the two words here, precision and recall. So precision here stands for precision is given as a ratio of true positives divided by the sum of true positives and fake positives, which is, so we get an intuition of how many true positives, that actual ground truth true positives there are. And recall is nothing but the ratio of true positives to the sum of true positives plus false negatives. So yeah, MAP gives is a really important metric for measuring how well we're doing with our network. So let's see the results. So as you can see in this table, these are the traditional methods of object detection, and this here gives the information, the MAP values of RCNNs. As you can see, for all of these classes, the values of RCNN are way higher than what the traditional methods give us. And here are the results of another classification dataset, IL SVR 2013. These are all uh, the metrics from the competition, the participants in the competition, whereas this is the metrics of the RCNN dataset on the same RCNN algorithm on the same dataset. So it's pretty evident that RCNN performs way better than the other values here. Opinions and comments. In this paper, the author makes some choices which really seem strange to me. The first thing is wrapping up the image. I think it would be since we are distorting the objects depending on how well the bounding box is selected. In my opinion, it would be more natural to just crop the patches around the bounding box for classification and keep the bounding box for actual reporting where the object is. So I think distorting the image is really a bad idea, and we would get way better accuracy if we just, you know, use the bounding box, the patch as it is. And the second thing which I would like to give my view on is the usage of SVMs for classification. Since the author is already fine-tuning the network in the target task, that is VOC, it seems more natural for me to just use softmax results directly than training SVMs for each of these layers.
Hi, I'm Manas. So far, Darshan has explained us the working of RCNN, but it's not that cool. Let's see how. The training in RCN is expensive in terms of time and resources. During the training of RCNN, each feature of the object proposal is extracted and is written onto the disk. Due to large amount of object proposals, the disk storage increases, and hence it's very expensive to store. Plus, since the convolution happens on each and every proposal, it's very time consuming. In RCNN, the training happens as a multi-stage architecture. It mainly happens in 3 stages. On first stage, the convolution happens on each object proposal. On second stage, SVM is applied on those features. And in third stage, the bounding box regressor is learned. And as Darshan told, the object detection is very slow. It's like almost 52 seconds per image. So a new algorithm was proposed. It was fast RCNN. So why fast RCNN? It was observed that the detection quality was improved in the fast RCNN. The process was streamlined and it was single stage training. And the training updates used to update all the network layers, and there was no feature caching. And because of that, it was very less expensive in terms of time and resources as well. So let's go and see some fast RCNN architecture. So in fast RCNN, how is it different from RCNN? In RCNN, each object proposal was applied convolution, but here the original image was applied with the convolution, and then with the help of region proposals, the output of the convolution layer is the feature map, which is fed into the ROI pooling layer. In the ROI pooling layer will be explained in the later sections in detail. The output of the ROI pooling layer, that those are the fixed length features, are then fed into the fully connected layers. The output of the fully connected layers are divided into 2 categories. One is the softmax classifier, which classifies the image, and another is the bounding box regressor. Now let's see how ROI pooling layer works. The main function of ROI pooling layer is that it converts the features inside any valid region of interest into a small feature map with a fixed spatial extent of some height and width. Here in the paper they have used the height and width to be 7 cross 7. ROI pooling uses max pooling to reduce the size of the region proposal. In the paper they have explained if the region proposal has the size more than 7 cross 7, how it is reduced. So let's see if we have an example of region of height 14 cross 14. So they have proposed by dividing this 14 by 14 into small grids of 2 by 2 and then taking the max pooling of all those images, which will give the final feature vector of 7 cross 7. In this way, any size of region proposal can be reduced to a fixed proposal of 7 cross 7. Now let's take a look on multitask loss. This is the main reason for the streamlining of the fast RCNN architecture. As we have seen before, we have the fully connected layers. The output of the fully connected layers are the softmax classifier and the bounding box regressor. The multitask loss is actually the jointly trained for the classification and the bounding box regression. The softmax classifier loss is denoted by this component of the equation, and the bounding box regressor loss is shown by this component. In this, we compare with the ground truth values of the classifier as well as the bounding box, and we train our model. Truncated SVD. For whole image classification, the time spent computing the fully connected layers is small compared to the convolution layers. But in case of fast RCNN, as we have large number of ROIs to process, almost nearly half of the forward pass time is spent computing fully connected layers. So they thought of using single value decomposition process. Let's say we have a weight in a fully connected layer of size u cross v. We can factorize this matrix into 3 matrices as shown in this, such that the size of these matrices turn out to be reduced than the original size. So truncated SVD actually reduces the parameter count from actual matrix size u cross v to t times u plus v. This actually increases the speed of the fully connected layers and hence is able to process the information faster. This simple compression gives good speed ups when the number of ROIs is large. Now let's have a look on the results. In this we compare fast RCNN, RCNN, SPPNet. This table was created keeping in reference of RCNN. As we can see, the training speed of fast RCNN is 8.8 times faster than the RCNN, and that is without SVD. With SVD, it's 213 times faster than the RCNN. In this result, we can see how SVD has actually speed up the processes. Without SVD, the time taken for the fully connected layers computation was almost 122 milliseconds, which was reduced to 37 milliseconds with the help of SVD. So according to me, there was a big improvement from RCNN to fast RCNN, and that was because of use of softmax instead of SVM, which increases the MAP, and significant reduction in running time because of use of SVD. But there was still one bottleneck in this network, which was selective search. This selective search, which provides the region proposal to the network, was actually taking a lot of computation time.
Hello, my name is Mayank. Now, so that you know about RCNN and fast RCNN, what if I say that fast RCNN is not that fast? It's still not a real-time object detector network. Here, the paper introduces a faster RCNN network. We will see how this affects the object detection process. Here, here in this graph which I have shown here on the slide, fast RCNN still takes about 2.5 seconds for region proposal. It is a dominating time of the testing time, and we will see if we can reduce this through using faster RCNN. Here, the region selection method is selective search, which serves as a bottleneck to this process, and we will see how we can reduce this bottleneck. Let's see. Now, visualizing the difference between fast RCNN and faster RCNN, the only improvement here is in the way region proposal works. Fast RCNN does use a selective search method, while here in faster RCNN we have introduced a region proposal method. There is a RPN. Here on the left you see there are fixed regions proposed by the selective search method, but RPN, since it's learning, it changes the network accordingly. RPN also shares weights with the base network, and hence it reduces the computation cost drastically. Now here we see how RPN works. Consider this as the feature map that RPN requires as an input. Here in the feature map we use a 3x3 sliding window over this feature map and generate anchor boxes for each sliding window. Let's say if we generate k anchor boxes for each sliding window for a feature map of size w cross h, we will get w cross h cross k feature maps, k anchor boxes. Right. Here in the paper, the author has taken 9 anchor boxes per sliding window, considering 3 for different aspect ratio and 3 for different scales. Here you see a sample of different anchor boxes of different scales and aspect ratio. We will see now how anchor boxes work. Here, anchor boxes reduces the requirements of image for multiple scales by creating anchor box of different scales and aspect ratio on the same feature map. So if we have a feature map, and instead of creating feature map of different scales, we just create anchor boxes of different scale from the same feature map 3x3 sliding window. Here, by using the anchor boxes, we ensure that if the object moves or translates, the anchor box will translate accordingly and the proposal will adjust. Also, because we consider different scales, here the proposals will be scale invariant as well. To get a better insight, let's look at the next slide. Here, at the bottom left corner, we see different anchor boxes of slides of different scale and aspect ratio. Creating this anchor boxes on an image, you see here a grid of anchor boxes, and if we create anchor boxes all over the image by sliding 3x3 window, if we have anchor boxes all over it and outside of the image. Now reducing the anchor boxes by discarding the anchor boxes that are outside the image, we reduce the number of anchor boxes that are proposed. Here approximately around 60k anchor boxes are proposed, and by discarding the anchor boxes which are out of the image and then further filtering the anchor boxes, we reduce it to around 2400 or so. Now about how we are going to get the loss function for this network. We use two types of losses here: classification loss and regression loss. Classification loss is due to the due to the misclassification by binary classifier here. Binary classifier assigns labels to each of the anchor boxes that we have created. It labels it positive if the anchor box here is with the anchor box that has the highest IOU overlap with the ground truth of any of the sliding window, and then if it has an IOU overlap higher than 0.7, and if it assigns also a negative label if IOU is less than 0.3. Also, only the non-zero anchor boxes contribute towards training. Here, this condition here of 0.7 IOU is sufficient to classify the boxes positive, but this condition above that has the higher intersection over union is to ensure that no cases are left. Now, going mathematically on how this loss function is, as explained earlier, loss function here thus has a classification loss, which is counted if whether the classified label is true, if this matches the true label or not. A regression loss, which is for if the predicted box thus matches the ground truth box or not. One thing to note here is that the regression loss only counts if the predicted label matches the ground truth label. Otherwise, this loss is ignored. Other major thing here is that both losses are normalized with number of classes for classification loss, which is the mini batch size 256 in this paper, and a regression loss are normalized by the number of anchor locations that are roughly 24,000 for this paper. Also, a weight term is introduced in this regression loss, which is around 10. We will discuss about this weight term further. Now, knowing about the loss function, let's see how we train the network. First, mini batches are created randomly with 256 anchors for each sliding window. That is, each sliding window may have more anchors, but we just consider 256 anchors randomly. The sampled anchors should have positive and negative anchors with a ratio of up to 1:1. Also, all new layers in the RPN are initialized with a zero mean Gaussian distribution with a standard deviation of 0.01. All the shared layers, which it shares with the base class, are initialized as a pre-trained model of our ImageNet classification as used in this paper. A weight decay of about 5 e to the power minus 4 and momentum of 0.9 is used as a standard practice. Also, a learning rate is divided. Also, the learning rate of 0.00001 is divided by 10 after 60k mini batches. With these parameters, the author has introduced three training methods for this network. First is alternate training method, other is approximate joint training, and non-approximate joint training. But these two methods, approximate joint training and non-approximate joint training, has their own disadvantages because of fixed weight proposal, and hence couldn't be implemented easily, and author goes with alternate training method. What alternate training method does is that with the initialized or the pre-trained base class, it trains the RPN network, and with fixing the RPN network, it trains this network again, the base network, and alternately then it fixes this base network and trains the RPN network, going this cycle, fixing alternate weights each time. It just trains the network simultaneously, both the networks. Seeing the experimental results here on the Pascal VOC dataset that we have used to evaluate the previous two networks. Here, RPN with VGG network with unshared weights, that is no weights are shared between the region proposal network RPN and the base convolution network. If we don't share any weight on VOC7, we get a MAP accuracy of about 68.5. Also, if we share the weights between these two layers, these two networks, we get a MAP of about 69.9. Here there are some more results with different data sets. Let's see about further. Evaluating this network on different settings of anchor boxes. Here we see that for just single aspect ratio and all three different scales, aspect ratio keeping 1:1, we get a MAP of 69.8, and with all three aspect ratios we still get a MAP of 69.9. So by reducing the aspect ratios to just one, that is not taking all the three aspect ratios, we can reduce the computation cost to some extent. Also, remember the lambda which we introduced in the loss function. Changing this lambda value doesn't affect the MAP much and thus can be ignored safely. This also says that the loss function wouldn't be affected much by the regression loss. Now let's compare all the three networks that we have gone so far. Now comparing them, now here we see that faster RCNN thus reduces the testing time for per image to 0.2 seconds from 50 seconds. That's a speed up of about 250 times the time taken by RCNN, which is really good.
Which is good by a big margin.
But still, MAP is not increased much. But this can be get by the intuition that we are still using the same detector network in all the three networks that we have proposed. The detector network is still the same. We are just changing the way in which that they are proposed. They are proposing the regions. Now, with knowledge of these three networks, we will see and we will implement this on our datasets, and Anirudh will explain you further.
Hi, I'm Anirudh, and now I'll be discussing about the experimentations we carried out. And yeah, this is the more interesting part of the entire presentation. So let's get to it. So basically, as in the beginning, I gave the motivation that we are doing the object detection for the for detecting umbilicus, banded, and wounds, so that we can localize the robot with respect to the patient to carry out the fast scan scans. So here the database is generated by taking images, by scraping images from Google, and some images were also taken from MedTech's website. So overall, I was able to generate 200 banded images, 1040 umbilical images, and 350 wound images. This was then, as the convention goes, split by 70-30 into train and test datasets. The training data was also further augmented by pixel translation, random pixel rotation, hue changes, saturation changes, image mirroring. All of these were random, and this helped me increase the training data by 6 times. So this is a short example of the umbilicus, the sorry, yeah, the kind of umbilicus data I had, the banded data. So again, here we are concentrating on the bandeds are concentrated in the stomach region, because the ultrasound scans are gonna be focused in the stomach region. But then, as you see here, it is not there. But then, because of the lack of images available online, I was considering some images which are not exactly in that region. Again, for wounds, because or not all wounds are in the stomach region, I have considered wounds which are out there. One more important thing here is I have restricted the band-aids to white bandages, and the wounds to gunshot wounds. This is again done to restrict the amount of database collection. Otherwise, if I just categorize wounds, then there is just infinite amount of data out there. Moving on, the architecture. So as we discussed, as all my other friends discussed about fast RCN and faster and normal RCN, and all of these networks require a base network. The base network I have, so I could have used LXNet, like ImageNet, or VGG trained on ImageNet as my base network, but I thought I should first even train that network on my images. Here the images I take are cropped images, so that the network is able to classify umbilicus, wound, and bandage. Again, the base network is the layers are from AlexNet, but then I train on these images and I pass on that network to my faster RCNN network later on. But before we go there, the accuracies for the base network are the maximum accuracy achieved for umbilicus is 98.3%, and for wound and bandage is successively 96 and 96.08 and 96.1. So here, one thing I would like to point out is for umbilicus is 98.3%. This will also later on, we'll see that the MAP, mean average precision, for umbilicus is higher, and having a good accuracy here is one of the reasons why we have a higher MAP later on. So as I said, mentioned, I passed this base network to the faster RCNN, and following the same theoretical, like the same theory, following the training process and the testing process, these are the final results we get on the testing time. So we have previously seen that the training time increased by 250 times and 50 times, but then here when I actually do it on my data set, the speed up in training time is by 1.7 times and 2.03 times. This I think is because first of all I have a different software system, because all of this is being done on MATLAB, and whereas and also there's just a single CPU. There's no GPU involved here. So of course, because of that, the speed up can be different. For testing time per image, here there's a significant increase of 36 times the original speed of RCNN for the faster RCNN. This is a significant boost, and this can be considered as real-time detection. I also have a GIF at in the end, which we'll see, which will see that how good the frames per second rate is. So yeah, moving on. Yeah, I know it's fast. So the network parameters. For faster RCNN, so basically I tried to keep the same parameters for all the three networks, so that when I do an MAP comparison, I can do I can say that the MAP comparison is accurate. So for the only difference is for faster RCNN, I kept the mini batch as 128 because it was actually giving me a better MAP, so I just thought on deciding on that. The momentum parameters is again okay. So yeah, the optimizer I'm using is SGDM, stochastic gradient descent. This is because for Adam it was taking significantly longer time. I don't know, it should take less time, but it was taking longer time, and I just got a better result with SGD, so I thought of going with SGD. Learning rates, yeah, E minus 3, E minus 4 is getting good accuracies with that. So okay, one important thing here is positive overlap range and negative overlap range. As my friends discussed earlier, this is the concept of IOU. So if my bounding box, the IOU is greater than 0.7, only then I will consider it to be a positive image. So yeah, this is discussed before, I just wanted to reiterate it. And again, negative overlap range is if it's between 0 to 0.3, it will be considered as a negative image. So yeah, negative region actually. So results. So I'm going to discuss the results for faster RCNN and in detail. When we have already seen how fast and RCNNs are compared. There's a decrease in all the three levels of it. So I'm going to give a brief discussion between the umbilicus, wound, and banded. So I see that the MAP for umbilicus is highest. I think this is I know this is because of the high training images for umbilicus, which is at least twice the images for bandits and wounds. So the high training images is of course a significant reason why I have an high MAP. Another important observation here was the incorrect predictions were more compared to the other two classes, but the missed predictions were very less. Like there were images where nothing was being predicted, but for umbilicus it was really less. And as I said before, the increased MAP is also because of the high classification accuracy we saw earlier for the umbilicus. So I think that is why we have a very significant increase of MAP of 0.66 as compared to the other two classes of wound and bandages. When I then compare wound and bandages, they both have very similar characteristics. Like even wound is does have a high contrast ratio when compared to the surrounding region. Even bandage has very high contrast compared to the surrounding region. But for wound, it's higher. I think this is simply because of the training data. Again, for wound, I have more training data than the bandages on the abdomen, and that's why I think it has a higher accuracy. Even if you look for fast RCNN, the MAPs are coming out to be the same here. So I guess it's just the amount of training data you're using. And the detection results, as we see, are given here. It's pretty good. Mostly all of them are being detected, but the boxes are of course different, and that is why the MAP is less. Also, yeah. Also, I want to discuss about the incorrect and missed predictions. So one thing I wanted to point out is that for a region like this was being considered as umbilicus a lot of time, like the belly button in this here. So the thing I was saying about incorrect predictions are very high for umbilicus. One of the reasons is this, that some of the body shapes may look like an umbilicus, and that is why there were a number of incorrect predictions for umbilicus, but mispredictions are very less. And as we see here, this looks like an umbilicus because of black region inside, and there's no blood here. So for practical cases, I think it really gets difficult, because then the images have to be very, very specific, because here if you'll see that the umbilicus is being detected as a wound, so because there's this black region inside, so sometimes it detects as a wound, sometimes it detects as umbilicus. Also, one more important thing to notice is both are circular in nature, so that can bring confusion into the network. So yeah, these are some of the networks. How can I improve this? Well, get more data. So it's just, I'm working on it. It's an ongoing project right now, and I'm trying to get more and more data to make these things better. And then I haven't applied on maximum suppression here, so I'm gonna do that and see how I'm getting the results. But yeah, this is the initial. So this is a video demonstration of the fast RCNN network which we implemented. We are detecting wound, banded, and umbilicus as we talked about before. This is a phantom on which we'll do an ultraprobe scan. It represents a human. So we see here that there is a wound here. So this wound here is very important because this is a fast scan position, and so the ultrasound probe will go like this on this position, and this is very important to it's very important to figure out where the wound is, because when the ultrasound probe will go to the fast scan position, and if there's a wound present, it is obvious that the ultrasound probe should avoid it. This is of the utmost importance if you want to make the system autonomous, and that is why the detection has to be pretty accurate at all times, and missing predictions is not allowed in such cases. So yeah, this was the implementation of this project. Now now we will go over some concluding remarks on all the three networks and some of the intuitions which we developed after studying all the three papers. So, in conclusion, after comparing all the three methods, fast, faster, RCNN fast, faster, and also experimenting with these three methods, I can say that, of course, faster is the best. But I also had a look at one-shot detectors, and then the conclusion here for object detection methods is that faster RCNN methods are more accurate, but the FPS, the frames per second, is still less, because one-shot detectors like YOLO, they outperform faster or CNN when you're talking about frames per second. So it depends upon the task. Then, if you want high accuracy, like in our purpose, where in purposes like medical robotics, then I think we should go with faster CNN. So yeah, that's there. Secondly, one of the intentions is that training the base network given to the faster RCN network, if we train them on the images which you want to detect, then it increased the MAP, like it increased our MAP by 2.3. percentage. So this actually helps. So yeah, that's the second thing which we noticed. And the third thing which we thought about after going over all the three methods is that what if we somehow use semantic segmentation and region proposals together? Like we are already training a network to give us 4 points, and which are then using regression laws corrected, right? But what if we use semantic segmentation, like we know the object locations, object pixels, and somehow use that to like that's how selective search works. It uses the segmentation to give proposals. So if we are able to use that somehow with RPNs, I think it should result into the next best detector which would be then faster RCNN or more faster RCNN. Yeah. So yeah. Yeah, that's about it. Thank you for watching the presentation, and if you have any other questions, feel free to send us an email. Thank you.